let's work through an example of computing a curve integral over a curve in R3. So we have our function f of x, y, z that's defined on R3 to be equal to x times y times z, and our curve C is given by the parameterization r of t equals 2t, 3 cosine t, 3 sine t, where t runs from pi over 2 to 3 pi. So this is a portion of a helix that's centered on the x-axis and essentially oscillates in the yz plane, or parallel to the yz plane. So here's a couple different views. The x-coordinate is here, and the y and z coordinates are the other two. So we want to compute the integral of f ds over the curve C. And just as in the case of a curve defined in the plane, we're just going to use this parameterization r of t in exactly the analogous way. So we need to know f of r of t, and we need to know the magnitude of r prime of t, both as functions of t, and this product is what we're going to integrate with respect to t from, in this case, t equals pi over 2 to 3 pi. So let's go through this. So we want r prime of t, which is 2 minus 3 sine t, 3 cosine t. And so the magnitude of r prime of t is the square root of 2 squared is 4, and then we get plus 9 sine squared t plus 9 cosine squared t. Now every helix with this standard parameterization will behave like this, and of course sine squared plus cosine squared is equal to 1. So in the end we get the square root of 4 plus 9 is the square root of 13. So the magnitude of the derivative vector doesn't matter at what point. The magnitude of the derivative vector is always constant. So the length of these tangent vectors are always constant for this particular parameterization. So that's particularly nice because it means this factor, the magnitude of r prime of t, is not going to make the integral any more complicated than what the function will do anyways. So now we need f of r of t. So that means we want f of 2t, 3 cosine t, 3 sine t. And so of course we just take the product of these three functions, and in the end we get, so 2 times 3 is 18, and then we get t cosine t sine t. So this is going to be the other factor of the integrand, and I'm going to use a trig identity right off the bat. This is 9t times sine of 2t. Sine of 2t is 2 sine t cosine t. So we'll just use a bit of trig there to rewrite that function. Okay, so now we're ready to plug in to this standard form, and so we get the integral from pi over 2 to 3 pi of f of r of t, which is 9t times sine of 2t, and then times the magnitude of r prime, which is always just the constant square root of 13. So this is the function we'll integrate with respect to t. So again, now we're working in R3, so we have three spatial coordinates, but in the end you use the parameterization of the function in an identical fashion as to the case of a curve in R2, and after you apply this method you end up with a single variable integral in terms of the parameter, in this case t. Alright, so in this case, to compute the integral, we're going to have to use integration by parts. I have the product of two functions. So I'm going to let u equal t and dv equal sine of 2t dt. Now, of course, I'm not worrying about the constants. They'll stick around. So then du equals dt, and v equals negative cosine of 2t over 2. Alright, so now using integration by parts, you can check that I get 9 times root 13, and then times, and then the antiderivative of this function t sine of 2t is sine of 2t over 4 minus t cosine of 2t over 2. So this is the function that we're going to integrate, sorry, not from 0, from pi over 2 to 3 pi over, not 3 pi over 2, pi over 2 to 3 pi. Okay, so we have this 9 times root 13, and then, well, for this term, when I plug in 3 pi, I get sine of 6 pi, which is 0, and when I plug in pi over 2, I get sine of pi, which is also 0. So this term doesn't really contribute anything. I get a 0 minus 0. On the other hand, here, what do I get? So when I plug in 3 pi, I get minus 3 pi over 2 cosine of 6 pi. Then I get plus pi over 4 cosine of pi. So 9 root 13, and cosine of 6 pi is equal to cosine of 0, which is equal to 1. So I get minus 3 pi over 2. And then cosine of pi is actually equal to negative 1, so I actually get minus pi over 4. Alright, so in the end, we were able to evaluate this curve integral, the integral of f over c ds, and it's because we can rewrite ds as the magnitude of r prime of t dt and plug in r of t into our function and turn this integral into a single variable integral. And so in the end, all these curve integrals will take advantage of parameterizations to rewrite them as single variable integrals, and then just do a little bit of single variable calculus to come up with the answer.